Greetings, Earth scientists. It's Mr. Gopal here, and I'm super excited today because this is when we start astronomy. Until Unit 9, Earth science concerns itself with phenomena on Earth, on planet Earth, the history of the Earth, geological formations, how they interact, how they change, how the Earth came to be, what it looks like in the present day. Now we're going to expand our view outside of the Earth to space. And so to start that process off, we have to look at the solar system and get a sense of why it formed the way it formed, what models we use to describe it over time, why the new model is better than the old one, and what that possibly implies about the future. Now, we won't cover all of that today, but we will cover some of those things eventually. But starting off, we're just going to take a look at the solar system. And so the focus question here, it's day 3 of Unit 9, Astronomy and Earth Science, is how is the solar system organized, all right? And if you watch this video and this video, what you're gonna see is that a lot of the conceptions that we have today about why we are here goes back to the theory of how we began. And that theory is called the Big Bang Theory. Now, I don't think I can do justice to the Big Bang Theory in this particular video, so suffice it to say that at the beginning, according to scientists who have theorized about the entire history of time, the universe was, almost like pin-sized, or maybe even smaller than that, an incredibly small ball that was incredibly energetic. The Big Bang Theory was an event where this ball exploded outward and started creating the still expanding universe. We can talk eventually about why scientists think that the universe continues to expand. At that point, it is expanding from almost nothing into a larger and larger shape. And this incredible energy ended up over a very, very long time. And you can see this particularly in this video. They do a good job of summarizing it. It's ended up expanding into galaxies, stars, planets, comets, asteroids, all of the things that we understand are various celestial bodies. When I say celestial body, I'm just talking about an object in space, and we can categorize those objects. All right, we live on a planet. The sun, which is at the center of our solar system, is a star. Okay, and so again, we want to understand why and how a celestial body spins, and then we want to contrast and compare the geocentric and heliocentric models of the solar system. And I'm going to explain why eventually we went with the heliocentric model. Finally, we'll expand a little bit more on the heliocentric model. All right. And to help us along with all this, before we get into these Regents questions that are at the end of the lesson, I'm going to turn to a guiding document that I made. Okay. And so the first thing that we need to understand is a little bit of vocabulary here. We have the term apparent motion, which the second video delves into in detail. Apparent motion is the motion that we see when we look at the sky. So if I look up at the sky, if I'm like out at the beach all day, let's say I stay there, I fall asleep and it's nighttime, or maybe I stay awake and I'm just hanging out at the beach for 24 hours. What I'll see is I'll see the sun come up over the horizon, and then it looks like it's moving across the sky and eventually setting, okay? And if that's all the information that I had about what's going on, then I could be forgiven for thinking that the sun is revolving around the Earth. Now, when I say revolving, I mean the Earth is here and the sun is traveling around it in some kind of circular shape, okay? So if that's all I had to go on, just the observations I could make with my naked eye of the sky, then that might be a simple conclusion to make, all right? And this is what the ancient Greek philosophers who started the, I guess, scientific field of astronomy thought, all right? They came up with the geocentric model. Geo is a prefix, it means Earth. Centric means center of, so geocentric together means Earth is at the center, all right? And if we look back at historical documents from ancient Greek astronomers and philosophers, we can see that they put the Earth at the center, and then they put planets and the sun revolving around it in perfectly circular orbits. Now, the perfect circle was less of a calculation and more of a theory based in kind of an idea of heaven. So it was, I guess, like perfection to think that heavenly bodies or celestial bodies would travel in perfect circles. And this is about as far as the thoughts went, okay? And so Plato, Aristotle, and Ptolemy were some of the philosophers in ancient Greece who were responsible for these contributions to astronomy, all right? And so they used apparent daily motion to conclude that the sun, stars, and planets revolved around the Earth, all right? However, fast forward about 1,000 years, and Nicholas Copernicus, a Polish astronomer, who again was not observing with very much more technology than them, seemed to reach the conclusion that no, in fact, what was going on was that the sun was at the center of the Earth, hence the name of his model, the heliocentric model. So we have centric, just like with the geocentric model, but we have helio before it, and that is a prefix meaning sun, meaning the sun is at the center, all right? And so Copernicus just had a theory about this. He wasn't able to elaborate on the why, but he thought, well, I think we're actually revolving around the sun, and so are the other planets. That's why it appears like they're moving. That's why it appears like we're moving. And you know what? The reason why it looks like the sun is revolving around the Earth is because the Earth itself is rotating. So it was brilliant observations that turned out to be verified once we had a lot more technology and mathematics and scientific theories to back it up. It just kept being proven true, all right? And so some of the people who made important contributions were Galileo Galilei, Johannes Kepler, and Sir Isaac Newton, all right? So the idea here is that first, Kepler was able to use geometry and increase technology of telescopes to make the observation that, wait a minute, at certain points during the revolution, planets are farther away and closer to the Earth. Now, how could that be if we're all traveling in perfect circles around the sun? So Kepler was the first to begin to do calculations to determine the eccentricity of orbits. And he concluded that the orbits of the planets around the sun were not perfectly circular, but they were elliptical. Additionally, he was able to prove another crucial thing that Newton came along and elaborated on later. He was able specifically to prove that at certain points during the revolution, planets seemed to slow down, and at other points, they seemed to speed up. Now, Newton came along, and along with Kepler's observations, he came up with the theory of gravity. The theory of gravity holds that all objects that have mass are attracted to other objects with mass, all right? And it's a very weak force, but nonetheless, it is a force between objects. And that the level of that attraction is determined by the masses of the objects and also the distance between them. Now, we know now that the sun is many million times more massive than the Earth, all right? Now, no wonder the sun is at the center of our solar system model, okay? Because the most massive thing would probably dictate the motion of far less massive objects, not the other way around. That just doesn't seem to make intuitive sense, all right? Not only that, but the points at which the orbits or the revolutions of planets was slowing down or speeding up corresponded to how close or far away they were from the sun. So when a planet was far away, it seemed to be moving a lot slower than when it was closer to, all right, closer to the sun. And of course, the orbits of planets that were generally closer to the sun at all times during the year, those orbits were much faster than the orbits of planets that were farther away, all corresponding to his theory of gravity, which held that the farther away objects are, the weaker the force of gravity is between them, and the less massive objects are, the weaker force of gravity is between them. So we have all this new evidence that helps us understand why we are among other planets that are revolving around the sun, and also why the planet is rotating. I'll finish with rotation because I forgot to cover it. All right, the turning of planets on their axes is called planetary rotation. And now we believe this goes back to the Big Bang Theory. So as I was talking about this energy explosion outward in the creation of galaxies, stars, planets, comets, asteroids, part of that blast was to put into rotation various celestial bodies, including the Earth. And this is the reason why it appears that the Earth is rotating counterclockwise, all right? Now, you might ask yourself, why has it never stopped? Well, there has been no counter force on it ever since. So scientists believe it's the concept of inertia. A body will continue to move the same characteristics, right? The same characteristics of motion as before, unless a new force is acted upon it. The only force that is acting upon it is the gravitational force of the sun. That is keeping it in an orbit, but it is not affecting the rotation on its axis. So I hope this has been a helpful introduction. I will post this document along with my video. And if you need a reinforcement on any of the terms at the beginning of this, take a look and keep this for your own notes. I hope this has been helpful to you. We'll continue to delve into astronomy, and I will see you all very soon.